Welcome everybody to new talk of the Holo Club. So today it's a pleasure to have Moshe Rozali, who's also part of the HoloTube team, who will talk us about, okay, sorry, let me say, he's from the University of British Columbia. And he will tell us about effective field theory for chaotic CFTs. So please, Moshe, whenever you want.
Okay, so a few things first. This is the first time I'm giving this kind of talk. It feels very, very strange. So please interrupt me often. If you feel like turning on the video, then I'll talk to some faces. And I apologize in advance to any sort of difficulties that we're probably going to experience. Good. So the other thing is, I kind of like this idea of HoloTube, of some ongoing seminar, so I thought it was a good idea, and I could help in any way I can. So I was kind of struggling a little bit about choosing a topic, because recently I've been thinking mostly about the black hole information paradox and disorder averaging in gravity and this sort of interesting things that came up. Which is not quite related to what most of you have been talking about or thinking about. So I chose to talk about some older work, which is maybe slightly more related. In particular, this work is based on papers with Felix Hall, and also with my excellent student, Wyatt Reeves. 2 papers and one that is coming. And I'm going to talk mostly about the earlier paper, just because it's a little bit more familiar context. It's a little bit easier to understand. Things got a little bit more technical and more into the language of abstract CFT a little bit later on. So I'm going to try to keep things a little bit less technical. The main character is going to be quantum chaos, which kind of it's a natural outgrowth of those of us who've been working on application of EDS to condensed matter physics. It's still something that condensed matter physicists think about a lot. But since, again, this is a little bit different from what many of you have been thinking about, I will spend a lot of time on introduction. Now, if the introduction is a little bit excessive, then please let me know and I'll go a little bit faster. Okay, and please interrupt me often with questions. Now let's see how I move the slide. Good, so this is the outline. I'm going to spend a lot of time on introduction and motivation just to explain what the context of this work is. In particular, I'm going to talk about the scrambling and out-of-time order correlators. That might be the part of the talk that may be a little bit more excessive introduction, since this subject has been beaten to death a little bit. But I will proceed, and you will interrupt me if I'm going too slowly. So the goal is to develop the mechanics to calculate those things in some sort of coarse-grained or effective description. And I'm going to give the paradigm for what I mean by that in talking about the soft mode in conformal quantum mechanics or 0+1 dimensional effective field theory. This is the start of all the subjects. It's the famous Schwarzian theory. It comes as the low energy theory of various models, including the SYK model, but I'm going to discuss it in the context of gravity as the boundary theory dual to Jakiv-Teitelbaum gravity. And from that point of view, it's very easy to derive and understand what it means to have an action for a soft mode, what it means for it to be a soft mode, derive the Schwarzian action and its coupling to matter, and see how it's related to chaos, which is what I'm going to discuss earlier. And right. So the aim was to understand this type of soft mode action CFTs, in particular in higher dimensional CFTs. But as I said, most of what I'm going to be discussing is the theory of soft mode in two-dimensional CFT. I'm going to proceed in basically the same order as in the introduction. I'm going to derive the action, or at least the parts of the action that we need to discuss chaos, namely just the quadratic action and the coupling to sources, and then describe how you calculate correlation functions using this formalism. There is an understanding of how to calculate more complicated objects, not necessarily related to chaos, which I'm going to touch on a little bit. But since this is not the main focus of this audience, I'm not going to discuss it too much. Then I'm just going to talk about the higher dimensional CFT in a couple of slides. There's actually an interesting understanding of various technical details of the two-dimensional case, even in reformulating dimensional CFT in the language that is more abstract CFT language. For example, the language of the shadow formalism. But again, since this is a little bit more technical and not kind of the bread and butter of this group of people, I'm just going to mention it briefly and maybe tell you a little bit what it's good for. And then I'm going to discuss future directions and maybe wildly speculate and see where we can, what we can do with all of that. Okay, good. So let's see. So basically the introduction has to introduce you to the whole big subject of quantum chaos, in particular quantum chaos in many-body system, which is even a more complicated subject. So let me just say enough to understand the context of this particular work and not dwell too much into it. So maybe the way to understand this is to kind of compare and contrast with classical chaos, which is more well understood and also maybe more well known from just undergraduate education. So the basic distinction I want to make is between the kind of short time manifestation of chaos and long time manifestation. So classical chaos is kind of, you can describe it by discussing trajectories in a phase space. If you start with trajectories with slightly different initial conditions, we know that there is the butterfly effect. So the divergence of trajectories in a chaotic system, or in one particular definition of chaotic system, nearby trajectories grow apart very quickly, exponentially fast. So this is something that's going to have something similar in the quantum context. Now, after the trajectories become farther from each other, if you wait for a very long time, then there is other set of issues to do with ergodicity. In some sense, the trajectories become dense in phase space, and if the phase space is compact, they just cover it densely. And that is the reason why statistical descriptions of classical chaotic system is a successful description. You can in some sense talk about averages over phase space as capturing late time quantities in classical chaotic system. But I want to just make the distinction that, you know, the butterfly effect and ergodicity are different issues, and that's actually something that persists in quantum system, either single particle, few particles, or many particles. So, good. So in quantum chaos, we have something now, following Kitaev, we have something now that's called out-of-time order correlators, which quantifies for you the butterfly effect, the well, there's no trajectories in quantum mechanics, but something similar to that, something that happens immediately that depends sensitively on initial condition. So this is a short time manifestation. They just tell you about short time manifestation chaos. There's also an older, especially in the context of single particle quantum chaos, there's an older body of literature to do with the long time manifestation of quantum chaos. And that's kind of a very strange situation in which, you know, those two maybe different eras talk about the same sort of thing using very, very different concepts. So usually when the old-fashioned quantum chaos concept have to do with statistics of the spectrum, or later on the ETH, which has to do with also eigenvectors of the Hamiltonian. There's some sort of statistical characterization of both eigenvalues and eigenvectors of the Hamiltonian. And somehow that random matrix or ETH applies to very, very long time, and it kind of replaces the idea of classical ergodicity. So whereas the Lyapunov exponent is very similar to what it quantifies in classical chaos, basically you can start with kind of well-defined trajectory and see how those trajectories diverge before they stop being well-defined trajectories. So because this is a short time, then in some sense, the classical and quantum concepts are similar, maybe not identical, but similar up to their first time. At late time, the concepts are completely different. If you wait for a very long time, quantum effects will take over, and the classical ergodicity, at least in a pure system with the classical ergodicity, doesn't play any role in the late time physics. So you need some new concept of what quantum ergodicity is to explain why statistical descriptions of the system is a good description at late times where you know that things thermalize. Okay. So quantum ergodicity is supposed to provide the foundation of quantum statistical mechanics, again, the statistical description of large systems. And basically, the idea is kind of encoded in the ETH, simple observable in a typical state, look thermal. It's not that you have to thermalize by necessarily coupled to an external bath. It could be a closed system. You don't have to talk about Gibbsian ensembles necessarily. You just talk about a single system evolving unitarily, but you probe it with simple observables that are kind of oblivious to all the detail of what's really going on. And if you do that, then statistical descriptions are good. Okay, so I think it's fair to say that the final thermal state is well understood, and the dynamics towards the thermal state is still not completely understood. For example, timescales to do with that dynamics, I think, are still maybe more difficult to explain from a microscopic point of view. And just the last remark is that this is not just a mathematical formalism to kind of pretty up some well understood physics. In the process of describing this, you find that not all the system, even complicated system with interactions, not all of them thermalized. There's something called many-body localization. So this is actually a study of physical effects and not just a mathematical exercise of trying to formalize some well-defined or some well-understood concept. Okay, so let me pause here for questions, just to make sure that I got everybody still on board. Any question, anybody? Okay, good. So this is the basic distinction in this in this transparency, this distinction between short and long time. So what the effective field theory that we're discussing here is going to try to encode is some kind of coarse-grained or effective, as the word is usually used, calculation of short time counts and out of time order correlators. But one of the nice or one of the interesting things, as you probably heard in other talk, is that in a holographic theory specifically, there is a connection between this type of description of the short time physics and the more familiar description of long time physics, namely hydrodynamics. So you know that towards when you look at long enough times, then basically the only thing that survives is the long wavelength conserved quantities, and they have a dynamics that's described by the hydrodynamics. And because this operates in a different time regime, it's a priori unrelated to what I'm discussing, but in holographic theory, there is a very direct relation. In particular, the modes that appear in both effective field theories are identical. This is, I think, an opportunity because you know, the holographic theories are very specific theories with very kind of fine-tuned properties, and it's kind of nice to be able to quantify precisely why that miracle happens. And here we have a clue. So one of the first such clues, and this is probably something you heard about, is that quantities that appear in these out-of-time order correlators, like the butterfly velocity, also appear or are also related to quantities that appear in hydrodynamic, like diffusion constants, etc. So this relation is a little bit mysterious, and in the context of this effective theory, this relation is even deeper and still mysterious. Okay, so we're going to restrict ourselves to CFTs just because that's easier to deal with, and we're going to talk about an effective scramblon theory. This is going to be an effective theory in the sense of being a truncation of the field theory that is sufficient to reproduce the effect that you're interested in, the out-of-time order correlator. There are also, this theory will also calculate those fine-grained out-of-time order correlator that Felix and myself talked about back in 2017, but I'm not going to harp on that too much. There's a series of longer and longer timescale associated with more and more fine-grained out-of-time order correlators, and we are able to calculate those as well in this effective field theory. Okay. Good. So as I said, I'm going to start mostly on talking mostly about two-dimensional CFTs. There's also a paper by Christian and Jordan. There's a series of papers by now on ADS3 gravity, which complete the story, including on the non-linear terms in action. I'm not going to discuss it in this talk, but this is useful to calculate interesting conformal field theory quantities like conformal blocks. So again, if you know what that means, one way to understand this theory is that this is effective field theory to describe the identity sector in large C conformal field theories. Okay. After discussing the two-dimensional case, I'm going to discuss a little bit higher dimensional CFTs. We are at the moment restricted to maximally chaotic system for reasons that I'm not going to discuss. So the conformal field theories that I'm going to discuss are going to be mostly in even dimension, and they're going to be defined on hyperbolic space. So this is the case where the conformal field theory in any dimension is still maximally chaotic. And we're able to show that, you know, there's a theory of a scramblon. It's an effective mode that captures this out-of-time order correlator dynamics. And again, furthermore, this scramblon is also related to hydrodynamic modes. Okay. In the higher dimensional case, there is a better or a more complete understanding of this effective field theory, and it's related to the shadow formalism. Okay. So I think this is more or less the end of the introduction. I probably took a long time, so let me pause for questions. Any questions from anybody? Okay, so let me continue then. So again, this might be the point that maybe discussing a little bit too much of those out of time order correlators. So please stop me if this is getting a little bit too familiar. Again, I'm trying to make this talk more or less self-contained for people who have not thought about this subject very much. So this out of time order correlator are all the rage for many years now. They were introduced by Kitaev. So let me quickly discuss them. They're sort of kind of intellectual cousins of various things. One of them I already mentioned. If you have classical trajectories and they diverge from each other at some exponential rate, this define a Lyapunov exponent, we'll see that there is a similar type of, if you want, quantum Lyapunov exponent that's defined by these out-of-time order correlators. There is a very strong relation to models of growth of operators. If you start with an operator that's simple and you subject it to Hamiltonian evolution, these operators become more and more complicated. In particular, if it's localized in some chain, it becomes more and more delocalized. And that growth is related in some very precise way to this out-of-time order correlator. There's also something called the Loschmidt echo. And for the interest of time, I probably will just skip describing what that is. So basically, you're looking for something that is a response of the system to an initial perturbation. So this is the usual linear response story where you perturb the system by some operator W at time 0 and measure the response by some other operator V at some subsequent time t, and to quantify the relation between the two, you take the commutator. This is how you find what is the relation between two operators. Now, once you have an operator, you want to see if it's large or it's small. You have to produce a number out of it. If you just take the expectation value, this is what's called linear response. The next thing you can do is to take the expectation value of the commutator in a thermal state. You put the minus for just static reasons. And that defines for you some quantity called C of t. Now, if the time t is long enough compared to the inverse temperature, then there's really only one interesting part of this, well, actually, two interesting parts of these four terms that you get for expanding the commutator. Two of them that have subsequent time 0, 0, tt will just factorize at long enough time and won't contribute to the connected correlator. So the really interesting part of this commutator, the expectation value of the commutator squared, I should say the absolute value of the commutator squared, if it and W are not necessarily Hermitian. The interesting part is the out-of-time order correlator where the times kind of interchange 0t, 0t. Okay, and this is the thing that quantifies for you the kind of Lyapunov exponent or the butterfly effect. For it to be meaningful, it has to be to start small. In order to, so this thing is bounded by some number of order 1. I think it's 2 for Hermitian operators. So in order to see some sort of growth, it's better start small. So in large N theories, it's kind of, in some sense, suppressed by 1/n. So it naturally starts at a low value, and then it has the room to grow. So the initial growth, so this is this follows a curve that starts exponential and then saturates. And the initial exponent is defined for you, the Lyapunov exponent. And then later on, there's some independently interesting dynamics where this moves towards saturation. Okay, good. So just a few comments. So let me skip some of those comments that are maybe not as interesting for our purposes. This out of order correlator starts very low and then it saturates, and this defines also a scrambling time, the time where it becomes order 1, and the scrambling time is of order log n, and famously this is something that you can also measure in black hole physics. And incredibly, the great growth of this Lyapunov exponent is bounded in quantum mechanical theories. And this is the famous result of Maldacena, Schenker, and Stanford. Okay. So I went a little bit quickly through this description because I'm assuming that this is something you heard about before. So let me pause again for questions, just to make sure that we are all on the same page. All right. So I'm going to assume that everybody is awake and carry on. So yeah, so as I said, so I want to calculate this in an effective field theory. I'm going to quickly introduce an effective field theory that does the job, just to demonstrate what I mean precisely. This is the famous Schwarzian theory that does it in the original context of the SYK model. And then I'm going to try to construct theories like that in higher dimensional CFTs. Okay. So most of the details of this part do not matter very much, but the final result is what I want to focus on. So one way to get into the Schwarzian theory is to just look at the low energy or low frequency dynamics of the SYK model or some other models that also have the same infrared dynamics. And the other one is to talk about gravity in 1+1 dimension, the so-called JT gravity. This is a simple theory of gravity. Because it's low dimensional, gravity is kind of trivial. In fact, gravity by itself has formally -1 degrees of freedom. You need an additional field for it to even be locally trivial. So it's not over constrained. So you do that and you add a dilaton. So this is a dilaton gravity. It has formally 0 number of degrees of freedom. That means that it's locally trivial. Every solution to the equation of motion is locally ADS2. This is very similar to pure gravity in 3 dimension with a negative cosmological constant where every solution is locally ADS3, but there could be still interesting global dynamics. And we are also going to couple it to matter fields. We're going to keep the matter fields non-fluctuating. There'll be external probes. So any solution is trivial. It's locally ADS2, and the dilaton is locally can be mapped in some coordinate system to the form 1 of a z, where z equals 0 is the boundary of ADS2. In other words, it diverges near the boundary. So the theory only makes sense if you put some sort of cutoff in ADS2. You don't go all the way to the boundary, and you put some boundary conditions on those cutoffs. And then the dynamics is that of the cutoff surface. So different solutions to the equation of motion are identical to each other locally, but they differ in the shape of the boundary curve at which you satisfy those boundary conditions. So in some sense, this is familiar from topological theories. The only dynamic is if you put the theory on a surface with a boundary, you have some edge modes. So you can think about the Schwarzian theory is the edge mode of this JT gravity. Good. So when you reduce this gravitational action, including its boundary term, into this dynamic of the boundary curve, the action reduces to an action for this soft mode T of U. T is the shape of the boundary as a function of some fixed variable U. So T of U is the shape of the boundary curve. So in other words, it's a diffeomorphism of the circle. The fact that it's a diffeomorphism will come in a little bit later. And you get the famous Schwarzian theory. It's a highly nonlinear theory. T prime never gets to be 0, by the way, so that's not a singular theory. And the Schwarzian action appears in many contexts, partially because it's determined in some sense only by symmetries. If you have a conformal field theory with a particular pattern of explicit and spontaneous breaking, which is the case both in JT gravity and in SYK and also in some other models, then you guaranteed to get that action. Okay, so this is the action. This would be the paradigm of what I call a soft mode action, in the sense that you can calculate those out-of-time order correlators without knowing the full microscopic physics, just by focusing on this one single low energy mode. Okay. Okay, so let me just very quickly demonstrate how would you go about calculate. This is a very highly nonlinear action, but you can do perturbation theory. You want to calculate those out-of-time correlators in a thermal background. So you impose the correct boundary condition by doing this transformation. You transform T to the tangent of some tau. That way you have the correct Euclidean time periodicity. I take the temperature to be 2 pi, and then you just do a subtle, you just do a perturbation theory around some solution. Tau u equal u is just a solution to the equation of motion. You can just see that that's the case, and you just perturb around that. And that perturbation theory just gives you a bunch of Feynman diagrams, and that Feynman diagrams, those Feynman diagrams will calculate for you correlation function, including those out-of-time order correlators that we're interested in. So this is maybe the simplest possible way to calculate perturbative quantum gravity quantities. This is the story that I want to replicate in the higher dimensional case. Good, so this perturbative more epsilon is what I would call the scramblon. So in particular, here's an example of just showing you that you can calculate its propagator. Okay. And also, if you look at higher order in perturbation theory, let me go back to the previous thing, then you can see that there's going to be interaction terms, self-interactions for those, for that kind of perturbative mode epsilon. So this is basically quantum gravity. You have a mode epsilon, it has a propagator, it has vertices. I'm not going to go into the details. They're not too complicated, but you can basically do familiar perturbation theory to calculate correlation functions. Okay. The correlation function that we'll be interested in is a 4-point function of some external operators that are inserted in order to measure this out-of-time order correlators. And I'm going to very briefly just show that that matter action. So those matter action describe the way that external matter, I'm not going to be interested in fluctuation of matter. So these are external probes. How do they couple to the Schwarzian mode T? So this is sort of a bilocal action because we insert 2 operators at a time. And then once we have that action, again, it's a very complicated action, but you can just do perturbation theory. So you can expand that complicated action in terms of this scramblon epsilon. And I called those interaction terms of the action as B's. These are just interaction vertices that tell you our external matter couples to this scramblon theory. So here's an example of what the B look like. To leading order, B1 couples to 1 power of epsilon, and B2 couples to 2 powers of epsilon, etc., etc. Okay, and for our calculation, we'll need B1 and B2. Good. Good, so I'm not going to look at the calculation in detail again for the interest of time, but I'm just going to say that you can calculate the out-of-time order correlators. There's this sort of a mini industry of calculating those in microscopic models. And this calculation is reproduced by calculating in the effective theory that I just described. So this is a particular perturbation theory, and you can calculate basically whatever you want, but in particular, you can calculate this Lyapunov exponent, and you can see that you find precisely what you want. So this is an effective theory in the same sense that you usually describe effective field theory. Basically, you truncate the theory to some finitely many modes, and you calculate what you want to specified precision, and you get the result of a macroscopic theory from that much simpler theory. But there's some mystery here, which is, there's two mysteries. First of all, the usual justification for the use of effective field theory is going to some sort of low frequency or asymptotically late time. And then you know what are the elements of this effective field theory. For example, at finite temperature, those are going to be conserved quantities on possibly some Goldstone modes if you have spontaneously broken symmetries. But here we're not going to asymptotically late times. We are staying at some finite times. And in particular, it's not clear what justifies the use of effective field theory in general. The other thing is, this is an effective field theory that's very intimately related to hydrodynamics, and there's no clear understanding, at least I don't understand clearly why that is. Not only that you get the effective field theory of a scramblon, but you also, the scramblon is basically related to a hydrodynamic mode. It's some sort of, if you want, analytic continuation of that mode. So the motivation to our work was this observation by Blake, Lee, and Liu, that what they call quantum hydrodynamics. There is a theory of an energy mode, which is a hydrodynamic mode, but it's extrapolated away from the long wave limit. And with additional structures, they show that in general, you're going to find that you reproduce the maximally chaotic Lyapunov exponent, the value that saturates the bound. It turns out that with this type of effective field theory, you are restricted to be maximally chaotic, but it's still interesting to see what else do you need to do to not be maximally chaotic. So our goal was to derive such theory at large C CFT and see what's the origin of this, this effective field theory. And as it turns out, this theory is also good to calculate other quantities, not just out-of-time order correlators. So I'm kind of running a little bit late. My talk at the 10, I'm assuming, right? So, or is that correct?
Sorry, you were asking about the time.
Yeah, it's more or less 10.
No, you still have almost half an hour.
I do? Okay. All right. So I won't.
20 minutes. We started very punctually. Yeah, let's say 20 minutes.
Yeah. Okay, that's fine. That's okay. So I won't panic as much. Well, I wanted it to be mostly an introduction. So I'm not going to go through all the details, but let me just flash precisely how we understand this kind of soft mode in conformal field theories, and what do we need to do to sort of constructively build that perturbation theory that I discussed before. So in the Schwarzschild theory, we had the full nonlinear theory. And in the higher dimensional field theories, maybe one way to understand it is that we want to build directly the perturbation theory and calculate those quantities that we're interested in. So basically what we want to do is to mimic the idea of constructing a theory of Goldstone-Moson. So what we identify, the ansatz for our soft mode, is a space-time dependent conformal transformation. So this is something that would be a symmetry if it was not space-time dependent, and therefore it's kind of a soft mode. It has arbitrarily low action if it becomes space-time dependent. So this is something that would be, for example, a theory of a Goldstone model. Now, in two-dimensional, you have infinitely many conformal symmetries. Basically, any holomorphic function, you can do a transformation. Delta z is epsilon of z for any holomorphic function, and that would be a symmetry. In order to make it space-time dependent, that means that this epsilon z is no longer holomorphic. It also has some z bar dependence. Okay? Now, similarly, we have some anti-holomorphic transformation, which we also promote to be space-time dependent with full space-time dependence, and they become soft mode. So they become gapless. So now, because they are related to conformal transformation, we know what their action. Okay. So for example, let me skip this idea of the Legendre transform. There's a way of formally doing what I said. I'm just going to skip that. So it's clear that basically you want to do a conformal transformation, but you want to make it space-time dependent. So that induces an action because T, the energy momentum tensor, is a generator of conformal transformation. To leading order, the quadratic action depend on the correlation function of two such stress energies. So your goal is to calculate the correlation function of these two T's, and those will define for you what is the quadratic action. The same idea comes about, the same idea defines for you what would be the cubic and quartic action, et cetera, You need to have more and more higher and higher correlation function of the energy momentum tensor. So this is the starting point of our perturbation theory. Remember, we started with some soft mode that had some quadratic action, and it had therefore some propagator you can calculate. You can do exactly the same thing that I discussed before in the context of the Schwarzian theory. You can, first of all, move to find a temperature in any conformal field theory. This is done by doing a conformal transformation. So this is cheap. And then you do perturbation theory. Before we started with the nonlinear action, we kind of expanded here. Here we sort of build this action perturbatively itself. Okay, so when you do that, you can calculate the action and you can calculate the propagator. We have done that. And the propagator in momentum space, in Euclidean momentum space, is what I write here. So this is very similar to the propagator that we had before. In particular, something that I won't harp on, but if you want to ask me about, there is this SL2 symmetries that appear in the Schwarzschild theory, and those actually are very interesting to discuss in any conformal field theories. you can see that because these propagators have poles, and you have to basically discuss how to treat those poles when you do the Fourier transform back to position space. Okay, so for example, if you do this Fourier transform, you get that the retarded propagator is this expression. And you can see that generically you will have exponentially growing behavior because the retarded propagator, that's first term there, that looks like e to the t. And therefore, if you use that propagator for correlation function, you have at least the chance of getting exponentially growing. The other thing that's still missing in this effective field theory is those external probes. We want to calculate 4-point function of some external operators in order to calculate the out-of-time order correlators. So we need to define those, and we have a prescription now to calculate those. You basically take their action in the absence of the soft mode, and you do a conformal transformation, a space-time dependent conformal transformation, so there's some action acquired, but you basically have a prescription of how to do that. And we can do that perturbatively in the strength of that conformal transformation or the soft mode. And we can define a matter action that's very similar to what we had before in terms of those B's. The B's are interaction vertices. They depend on the dimension of the external operator, H and H bar, and their location. And in fact, because in the Schwarzian theory, those couplings also come about from a conformal transformation, the exact form of those B's is basically identical to the one-dimensional case. And that's going to be also the case in higher dimension. Of course, they depend on more locations. So once you use them, they give you different answers, but the form of those vertices is very similar. Okay, so what we find when we calculate that, so again, the calculation is very similar to what we did before. We have Feynman diagrams. We have external operators coupling to our soft mode. We have the propagator of the soft mode, and we basically have an exchange diagram. So what we find is that we have a very simple calculation to, especially if we don't want the full 4-point function, but just the exponentially growing mode, it's really, really easy to get that. And we get the same out-of-time order correlator that's calculated before by Roberts and Stanford. We calculate both the Lyapunov exponent and the butterfly velocity. Now we have spatial dependence, so you can also ask about how chaos propagate in spatial direction. In CFTs, it really has to be the speed of light from conformal invariance, so maybe that's not very surprising. We get the right answer. We also got the pole skipping phenomena that was discussed by this paper by Blake, Lee, and Luke. So let me pause for questions. If anybody has any questions at the moment. All right. So this is basically everything that I wanted to say. Let me just make comments and maybe discuss a little bit the higher dimensional case. Okay. So more comments on the effective field theory. This is this effective field theory was constructed in the Schwinger-Keldysh contour. Maybe in this particular case of two-dimensional CFT, that's not as significant. I think the SL2 symmetries, again, I'm trying to keep things not very technical, but they're very interesting to discuss in higher dimensional CFT. They generalize those of the SYK or the Schwarzian theory. They also include the shift symmetry of Blake et al. And I think we only understood them really when we started discussing the higher dimensional case, where it's part of this beautiful story of the shadow formalism. Okay. And the final thing is, even though this is not my focus here, I'm trying to talk about mostly this out-of-time order correlators. You can calculate other quantities using this effective field theory. And generally speaking, this Euclidean action or this action is useful as a theory of the identity conformal block in large C CFTs. So we calculated the conformal block, at the 4-point conformal block. There's a nice paper by Felix and Tarek Hanous that calculate the 6.1 in the particular channel. It seems to be an effective way of doing that. There's various ways of calculating those quantities in CFTs. So I'm not really sure how this is competitive, but it is at least familiar way of calculating things. You want to calculate, for example, 1/c correction, you just calculate one with diagrams. So there is a systematic way now of calculating conformal field theory quantities that are by and large now calculated using more algebraic quantities. So I wouldn't say what is more transparent or what is easier. I have less background in those methods, but Feynman diagrams are familiar at least. Okay, so this is mostly what I wanted to discuss in this forum. So let me just discuss the paper that we wrote about high dimensional CFTs. We also have some work in progress. So I'll be brief. So basically, I already described what we need in order to construct this effective field theory. We identified the soft mode. We conjecture that this is a space-time dependent conformal transformation. We perform this conformal transformation perturbatively and see what is the resulting action. The resulting action will involve basically correlation functions of the generator of conformal transformation, which is the energy momentum tensor. So this in principle can be applied to any CFT. But the easiest thing to do if we want to work at finite temperature is to work on CFT on a hyperbolic space. The reason is that this trick that I did of the conformal transformation to move from 0 temperature to finite temperature only works in a higher dimension if you're kind of compromise and say that your spatial direction is hyperbolic space. And then you have a conformal transformation that maps you to a finite temperature, where the temperature is fine-tuned to be the same as the radius of curvature of that hyperbolic space. Okay. So then you can use a correlation function in vacuum to describe fine temperature physics. Otherwise, it will be a little bit more complicated. So we discussed specifically that theory. That theory is still maximally chaotic. We seem to be still restricted to the maximally chaotic case. We calculated the butterfly velocity as was calculated previously by Perlmutter and confirmed it's the same one. And just as you might expect, in even dimension, the soft mode gets its action from the conformal anomaly, at least in the order that we discussed. Okay. We can also understand the soft mode using the shadow formalism. There is a way of projecting into the identity sector by using the energy momentum tensor in shadow. And one way to understand our soft mode is as related to the shadow of the energy momentum tensor. It turns out that the shadow, and this is probably going to not be useful for too many people, but let me just say that sentence. The shadow turns out to be a total derivative, so you can just write it as a derivative of some operator. That operator is a non-unitary operator. It has dimension -1, and that's exactly our soft mode. We saw that this is identical to the other way of thinking about the soft mode as a generator of a conformal transformation. So this is generalized the soft mode in 2-dimensional, if you want, the 2-dimensional Polyakov action that could be written as a local action using a particular definition of the soft mode. Okay. Good, so let me conclude. This was just flashing very quickly the higher dimensional CFT and the fact that we can do the same thing as we did before. So So possible direction for future research. So the most ambitious thing is that it turns out that this kind of effective field theory describes necessarily maximally chaotic case. And one of the reasons why this work, I think, could be interesting is that it's there to illuminate maybe what's so special about holographic theories, and in particular, that mystery that in such theories, the late time regime described by hydrodynamics is also useful for the early time regime that calculate the OTOCs. Clearly, in order to really understand that miracle, you have to understand what happens in more generic case. And in particular, you can discuss things that are not quite maximally chaotic, but almost maximally chaotic, and ask what new ingredient is useful. Those theories are kind of stringy in the bulk. So in some sense, you're kind of starting to look at stringy effects of those in those effective field theories, and what new ingredients you need in order to discuss such theories. And we tried various things. I think it's fair to say that none of them seems to be doing the job at the moment. One thing that we're writing at the moment is, so the thing that we did in two-dimensional is a closed form non-linear completion that was discussed by Kristen and Jordan. You can, in some sense, do the same thing in higher dimension. In higher dimension, conformal symmetry doesn't give you the full information about the theory, so but it gives you some partial information. So we're kind of hopeful that this theory will be good for some specific questions. So we're looking for those applications. The effective field theory, as I said, is effective in calculating conformal blocks, including corrections, including higher blocks. And I think the question is how much easier, or is it easier for calculating these quantities comparable or better than existing methods? And then there's various other things that you can sort of start to think about based on this analysis. So good, looks like I concluded in time. So yeah, please ask questions.
Thank you very much, Moshe.
So, I have a question.
Yeah, go ahead, Luke.
About the higher dimensional case. So as you explained, you have to focus on, you have to work in hyperbolic space for the conformal map to work. But this also means that correlators, that thermal correlators are basically fixed in terms of, zero temperature correlators. So it's not really what we usually mean by finite temperature physics in that sense. And in particular, you don't expect to have a hydrodynamic regime in this type of theory, meaning the late time physics won't be, won't have the usual hydrodynamic description. So, so my question is, well,
it might. Yeah, it might be. I mean, in two dimension, when you do the same thing, you get the theory of finite temperature, but of course, it's not really hydrodynamics. It's right. Non-dissipative. Right. So it might be a similar statement here. Certainly, it's not a dissipative theory. Right. But one of the things that we're trying to see is, whether this story of non-maximal chaos is related to the fact that we get very, very specific. It's formally hydrodynamics, but it's really non-dissipative, so it doesn't have the physics of hydrodynamics very much. Mm-hmm. It's hydrodynamics in the sense of being the theory of the energy momentum tensor, basically.
Mm-hmm. And do you have any hopes of doing this in different, say, flat space, finite temperature?
Well, that's related. So in this particular case, in those cases, this is not a maximally chaotic theory. So one way to see what happens in the non-maximally chaotic case. So this structure, if we don't break any of the symmetries and we just write the theory of the soft mode, there's a paper by Hong and collaborators that show that the Lyapunov exponent is necessarily maximal. So something else has to come in. So, you know, one way to do it is to just postulate something. The other way is to just look at a particular example and see basically which of the assumptions does not hold. I mean, dissipation seems to be a natural thing to check, but I mean, I don't think that it quite gives the same sort of the thing that we hope for. So flat space might be the example to look for, but we're kind of biased to think that, oh, there's some background noise. We were kind of biased to think that maybe the easiest thing to look at is something that is not quite chaotic, but is almost. But maybe flat space would be another way to do it. Basically, you need to have some control over a correlation function of the energy momentum tensor in order to kind of discuss that physics. And perhaps in flat space, you don't have enough.
Okay, thank you.
Sure, sure.
Martin had a question, I think.
Yes, thanks. So thanks for this nice talk. I've got a question regarding your comment about this effective field theory being a nice tool for calculating conformal blocks. So yeah. I'm wondering, so basically you listed two things which people can look at, higher point or 1 over C corrections. That's right. Can you also comment whether it's possible with this nonlinear computation of this EFT to compute, say, conformal blocks in a Lorentzian setting for very late times? Because I think this is really an...
yeah, we thought about that a little bit. So there's a paper, I don't know if you discussed that, but depending how late is late time. So if you talk about times of order, the central charge, there's this beautiful paper by Per Krauss and collaborators. So in principle, the effective field theory should be able to calculate that, but you have to resum a set of diagrams. Like even to calculate the time of order, the log of the central charge, which kind of starts seeing saturation of the OTOCs and things like that, you need to sum over ladder diagrams in this effective field theory. So multiple exchange of the soft mode. But simple exchanges don't involve any self-interaction. If you do that, then you get, for example, the familiar story that the conformal blocks exponentiate in large C CFTs. The way it comes about in this effective field theory is because in order to get this conformal block, you sum over infinite number of simple diagrams, the exchange diagram. Now, the conjecture is that for those late times, you would need to find some resummation scheme of this effective field theory exchanges, some sort of diagram, or equivalently some sort of Schwinger-Dyson equation to generate those diagrams, and that will reproduce that result, or maybe even generalize that. So, you know, there was maybe a few days last year where I tried to think about how to get that effect. That's something good to think about, I think. But again, I think you need to kind of have an argument that at those late times, there's a particular set of diagrams that dominates the physics, and then you can resum those diagrams. I mean, because there is kind of a well-defined, interesting answer there that was found by Hare. I'm hopeful that there is a story like that, but certainly I haven't been successful in it as much as I thought about that.
Let's see, any more questions?
If I may, I have a rather general question.
Go ahead.
So you mentioned in your introduction that the early time regime, the quantum chaos is in a certain sense similar to the classical chaos in a sense that what I understood is what you meant is that the Lyapunov exponent describes the exponential growth of excitations. Is there a precise?
Well, this was more like in the single particle chaos, just a quantum mechanics. I think this is maybe a little bit more complicated in the many body system, but in the single system, you know, there's no trajectories in phase space, but you can start with some sort of Gaussian wave packet. It is approximately localized, and then, you know, because h bar is not zero, then it kind of diffuses. So now it's a competition of effect, right? On the one hand, those trajectories that are well-defined stop being well-defined after a while. On the other hand, the trajectory diverge. So, you know, if you look at short enough time where the trajectories are still well-defined, you get basically the classical answer. Another circumstance where you get the classical answer is, as you should, is where you couple the system to some external system and you get decoherence. And in that case as well, you know that the classical result should hold on general principles. So you should be able to define a Lyapunov exponent if you have a decohering system. I think those stories, as far as I understand, maybe are less understood in many body systems.
Thanks. And as maybe a follow-up, I mean, everyone is interested in the connection, as you mentioned, between the early time and the late time. So could you comment on the late time behavior, how it is different in the quantum chaos from the classical chaos? I guess you kind of gave a partial answer definitely already.
Well, I mean, there's a beautiful paper by Michael Berry in the old days that he discussed basically that story. Basically, he says that h bar goes to zero and late time are limits that don't commute. And basically, as soon as you turn on h bar to be as small as you want, then the late time behavior completely changes. So in some sense, classical ergodicity, again, I think it probably is still in effect in some decohering system, but I think for a closed system, classical ergodicity does not play a role, I would say. And there's something else that comes about, and that's something else because quantum mechanics is so different, so it's something else as a different flavor. Spectral statistics, random matrix theory, this sort of thing. But yeah.
Thank you.
Yeah.
Thanks a lot.
I wish I could remember. Yeah, I wish I could remember that the name of that paper. Anyway.
I'll look for it. Thank you.
Thanks, Matthias. Okay. Any final question, comment? Okay, if not, let's thank Moshe again for this very nice talk.
Thank you.
And that's all for today. So we are back next week, back at 16 Central European time. So have fun. Thanks a lot.
Thank you.
Bye, Moshe.